In activity 5.6, we're going to go through a few examples of applying the first and second fundamental theorem of calculus to some examples. Now here, this is a perfect example of the second fundamental theorem of calculus because what we're doing is we're taking the derivative of basically an antiderivative. So these are basically acting like inverse processes, and what's going to happen is via the fundamental theorem of calculus we would use the antiderivative of this, plug in this upper limit and this lower limit. But then we would take the derivative of that, which would get us back to where we started, and the part where we put in the constant is going to be 0. So very quickly we see that this is actually just going to be e to the x squared, as that'll be the derivative of this function. Remember, this is a function with respect to x. T is just a dummy variable. So taking the derivative of it with respect to x just gives us e to the x squared. Now here we're going to apply the first fundamental theorem of calculus, because what we need to remember is an antiderivative of d dt of this is t to the fourth over 1 plus t to the fourth. So we have t to the fourth over 1 plus t to the fourth, and then we apply our limits, negative 2 to x. So in putting those in, we're going to have x to the fourth over 1 plus x to the fourth minus, now we're going to plug 2 in. 2 to the fourth is negative 2 to the fourth is a positive 16 over 1 plus 16. And so we're going to have, just simplifying just a little bit, we're not going to worry about common denominators. X to the fourth over 1 plus x to the fourth minus 16/17. So this is a perfect example of the second fundamental theorem. This is a perfect example of the first fundamental theorem. In C here, we can see that it's going to be a case of the second fundamental theorem of calculus, but notice that the x is underneath. So we're going to make one step. Remember to switch those limits. All we have to do is make our integral negative. So negative 1 to x of cosine of t cubed dt. And now we can apply our second fundamental theorem of calculus, which says this is negative cosine of x cubed. So it's a pretty nice little theorem for these type of problems, and it has a lot of power moving forward. A couple more. Once again, this is going to be a case of the first fundamental theorem of calculus. So again, the antiderivative of this integrand is ln of 1 plus t squared. And we're going to go from 3 to x. So we're going to have ln of 1 plus x squared minus ln of 1 plus 3. So ln of 1 plus x squared minus ln of 4. Or if we wanted to apply a property of logs, we could rewrite this as a single log, ln of 1 plus x squared over 4. Last example, the first one that we see where the upper limit is something other than just x, in this case an x cubed. This is going to be actually a chain rule, because what's going to happen is we're going to plug in that x cubed for t, but then we're going to take the derivative of it. So we have a chain rule. So what's going to happen is we're still going to have that substitution. So sine of x cubed squared times, now this is via our chain rule, the derivative of x cubed, because that's our inside function. So we get 3x squared sine of x to the sixth for our final answer. So if one of your limits is more than just x, realize that's going to be a situation where you have a chain rule, because basically that's like a composition of functions.